Yes. I haven't put the ads up. Oh, yes, I have to. Once Mikkel's done the test, if he finishes early enough, I can mark it and we'll get our matrices test back. I put them into Power School. I have not added the bonus yet, so we'll have to check that as well. Okay, here we are. Interesting results. Here's the first interesting result. If you do the dot product of something, you will get the same answer as if you found the length of that vector and squared it. So if you do the dot product with its own vector, you will get the same as the length of the vector squared. Now that's not too crazy, because how do you figure out 2, 3? How do you figure out the length of it? Well, you just do a squared plus b squared, right? And when you do the dot product of the same thing, you would just get, that would be squared, and that would be squared, and you wouldn't have the square root sign. So this follows naturally. So that's kind of interesting, but really important is this result. The dot product of two vectors happens to be the same as the length of one of the vectors times the length of the other vector times by cos of the angle between them. So if I have some vector u and another vector v, Ichi has arrived. Okay, so if we took the length of u and multiplied it by the length of v, and then took cos of the angle between them, it just so happens that that's exactly the same as the dot product. Now what this means is that we can do, even in 3 dimensions, we can figure out the angle between things a lot quicker and a lot easier than we used to. How did we used to find out this angle? Let's say this is 5 and this is 8, and you wanted to figure out, oh, it would be more than that. If you knew these two vectors, 5 and 8, you would have been able to also figure out that vector, right? Because you could just take this one minus this one to find that vector, right? And say you knew its length as well, it happened to be 10. 5, 8, and 10. How did you find this angle in the past? You'd use the cosine law. Right? And you would have that 10 squared equals 5 squared plus 8 squared minus 2 times 5 times 8 times cos theta. Okay? Rearranging this formula, and I'll leave this for something for you to try to see if you can figure out. But rearranging this formula can get you back to this result. This is the length of u, this is the length of v. See if you can rearrange it on your own and get that result. Now, once they realized that result was there, you can actually do a lot of math a lot quicker and a lot easier than you used to. You can also tell in either 2 dimensions or 3 dimensions if vectors are perpendicular really easily. Because you know that if they're perpendicular, The angle is 90 degrees. So you can just say, well, if my dot product is 0, then I'll know right away that those two angles are perpendicular. Here's a new perpendicular word for you. How many people have heard of this? Da, 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 da. That word for perpendicular before? Orthogonal? If cos is bigger than 0, because lengths, remember, just write it up here again, u dot v is equal to u, length of v, cos of theta. Because cos is positive in quadrant 1 and cos is negative in quadrant 2, that if the dot product is positive, you know that it's an acute angle. Because the length of u and length of v, since those are lengths, will always be positive. And if all of a sudden you have cos less than 0, in other words, if the dot product is less than 0, you'll know that you have a bigger angle, that you know you have an obtuse angle between them. And you can rearrange this formula, and now this will be an easier way to calculate the angle between two vectors rather than going to the cosine law. Because you can just use the positions. You don't even have to figure out where they are. Plug things into the formula, quickly get their lengths, quickly get the dot product, and you'll be able to figure out the angles between things in a much quicker way than our old analytic geometry did for us. And because it's so quick, it applies to 3 dimensions as well and beyond, although there's not too much realistic stuff that you have to figure out the angles in 4 dimensions between two things. But it's a really, really powerful result. Okay, so let's do some examples. And